today I'm basically going to go a bit more into the detail of how we actually use X-ray instruments to do science, basically. Okay. So just to put things into a bit of like historical context, just a quick question. Who can name either of these two people? Anyone? Kepler? Shakespeare? Any other guesses? No? Okay. Who said that? Yeah, okay. So, the guy on the right is Galileo, right? And he's largely known for effectively starting modern day optical astronomy by creating the first telescope. But the guy on the left, closer? Okay. The guy on the left is Hans Lippershey. I still forget his surname. But this guy, 1 year before Galileo, is actually known for having the first patent of a modern day telescope. But for the purposes of this talk, the key, most important thing is the date. So modern day optical astronomy, in which we used instruments to record the sky in optical light, started in the early 1600s, right? So optical astronomy is 420 years old at least, right? Possibly even older. But what if you were to try and take an image of the sky from the ground in X-rays? You ready for the high definition image? This is what you would see, okay? This is the best we can do from the ground for imaging the sky in X-rays. And it's not a trick, there's nothing there. Because thankfully for us, the sky absorbs X-rays in every direction, so we don't get fried. But unfortunately for the X-ray astronomers in the house, it makes it very difficult to try and actually observe anything in the first place. So what do? So as early as the 1940s, so still pretty recent, scientists realized that the best way to avoid the atmosphere, if you want to detect X-rays from astrophysical sources, was to effectively escape the atmosphere. So the first experiments that did this were called sounding rockets, and the whole point that they're called sounding rockets is because it comes from a nautical term to literally mean to take observations, right? And so it was just effectively a Geiger counter that could detect X-rays incident on them, and those Geiger counters would be launched 30 to 90 miles into the sky to avoid most of the atmosphere to the point where you can start to detect X-rays. And until 1962, everything that we knew about in X-ray astronomy is encompassed in this source right here. The only thing that we knew that emitted X-rays in the sky was the sun. And that was detected for about 20 years from these various different Geiger counters that basically got sent up on a rocket, right? This is a much more updated image in X-rays, where red, green, and blue show increasing energy in X-rays. And it's a pretty incredible image. This is not the sort of data back then that people would have got. But what happened in 1962? So this plot is basically the equivalent of if I were to show you the first sort of diagram that Galileo took of Jupiter and the moons, right, for X-ray astronomy. So if that image of Jupiter with its 4 main moons is sort of the bridging and the starting point of optical astronomy, this plot here is the start of X-ray astronomy outside the solar system. So what this is just like the previous image. This guy, Riccardo Giacconi, was responsible for a sounding rocket that went up in 1962, and the main aim was to try and find out if X-rays from the sun get reflected off the moon. But what they actually found is this plot here, right? And so what this shows is on the x-axis, it shows the direction that the Geiger counter is pointing at any given time during the flight of the mission, and on the y-axis, it shows you how many X-rays were detected. And so two very interesting things in this plot. One, you can see this massive peak, and this peak was exactly what Margaret was talking about earlier. It's one of the brightest X-ray sources on the sky, and this is an accreting neutron star called Scorpius X1. Right? It emits a crazy amount of X-rays. But for the purposes of this talk, what I find particularly interesting is what's known as the background. Right? So you can see that for a 360-degree view in this plot, this pinky line that I've plotted never goes down to 0. And the reason for that is that in every single direction on the sky that this instrument was pointing, it was always detecting X-rays from some kind of source. And for about 4 decades, there was a mystery as to what was actually generating this flux of X-rays in every direction on the sky that was never detected before. And just to say that this essentially this work in 1962 was awarded the Nobel Prize in 2002 for essentially starting X-ray astronomy as a field in itself. So modern day X-ray astronomy outside of the sun started in the early 60s, right? So it's about 60 years old, compared to optical astronomy, which is over 400 years old. Okay, so what is this X-ray emission, right? So this is a sky map. If you were to reorient all of the coordinates of the sources that you see on the sky, such that the Milky Way goes straight through your coordinates, it's called galactic coordinates for obvious reasons. And what you can see here is it's essentially an extremely sensitive image by the optical instrument Gaia, which is the European Space Agency's star tracker, essentially, of the Milky Way. So it's tracking billions of stars throughout the Milky Way to try and pinpoint exact locations of various astronomical objects. So this is just to reorient. You can also see in the bottom right there the large and the small Magellanic Clouds, which are also very close to the Milky Way. But if you were to have an equivalent image in X-rays, this is what you would see, right? So this is the latest sky map from the eRosita satellite, a German-led team that mapped the entire sky in X-rays. This is relatively low-energy X-rays, but you can see a whole bunch of other sources. Just for the record, this extremely bright blue object in the sort of upper part of the center, this is Scorpius X1 that was detected in 1962. This is that crazy bright source. But you also see a lot of for extragalactic astronomers, contaminants and noise in the foreground coming from the Milky Way. But if you look outside of the Milky Way through the center, you can see all these points, right? You can see lots of points, and you can see that they're uniform, they're constant, they're always the same regular pattern away from the Milky Way. And so what that tells you is that whatever's generating this omnipresent glow of X-rays, this X-ray background, it has to be outside the Milky Way, right? So it has to be extragalactic in origin. So for a very long time, it turns out that just because of the physics of it, there are only two things that could actually generate this X-ray emission as we were seeing it. And so these two things were either there was a hot plasma that pervaded the universe through all of the galaxies out there, and it was so hot, like millions and millions of degrees, such that it would emit a huge amount of X-rays that we would see on every point on the sky. And the characteristic of this hot plasma would be that there were no point sources. We were just seeing waves of X-rays coming through from thermal hot emission. The other option is that our X-ray instruments just weren't sensitive enough, and actually it's a whole bunch of point sources that are unresolvable with current instrumentation. Right? It wasn't until the cosmic microwave background was discovered 2 years after the X-ray background, and then studied with the COBE instrument, that people actually realized that the cosmic microwave background, which is the afterglow of the Big Bang, was extremely constant on the sky, and it was far too constant to also be situated with a hot plasma, because it turns out that a hot plasma would knock all of the electrons around, and you would end up seeing a sky map of the cosmic microwave background that would just look like a hot mess. Right? And so because COBE found that it was so constant, it meant that it just could not be a hot plasma that pervaded all of the galaxies in the universe. So what does that mean? It means that we just didn't have a good enough telescope, and it means that we just needed to get a bigger one. Okay? And so, to go from this and resolve that background into the individual point sources that make it up. So, there are a few ways to detect X-rays. Probably the most sort of common before instruments like Chandra was to actually use what's called a collimator. And so the idea was that X-rays are extremely hard to stop, they're very energetic, and so what you do is you basically have a thick piece of dense material like lead, and you cut a very distinctive pattern into that lead, and then it casts a shadow onto your detector. And because you cut such a specific pattern, it means that you can roughly localize where a source comes from depending on the shape of that shadow that lands on the detector. Right? You can sort of reverse engineer it. The positive of that is that you can look at huge contents of the sky, huge areas of the sky, but it's not very sensitive for making images and resolving point sources that we would need for the X-ray background. So the alternative is to try and focus X-rays. Now, this is an extremely difficult task to try and do, right? Because if you were to just have, much like the telescopes today, the reflector, if you were to put a reflecting surface in front of some X-ray photons, the X-rays would go straight through, or they would just be absorbed, right? And it's a really big problem. But then a very clever guy called Hans Walter discovered that you don't necessarily need to just stop the X-rays, you can guide them onto a detector. If the detector's thick enough, all you really need your mirrors to do is to sort of skim the X-ray light, much like you're skimming stones over water. You only need to just guide them onto your detector. You don't need to actually reflect them. And so to do that, all modern day X-ray images are taken by instruments that look like this, where the mirrors, instead of having a dish, you actually just have round, almost barrel-like mirrors in which these X-ray photons are guided onto the detector. So what did this look like for Chandra? So Chandra is a bit unique, well, extremely unique, in the sense that it is the most sensitive instrument for taking X-ray images that has ever been built and will probably ever be built for a good decade or so. And how did they do that? Well, it may sound relatively simple, but firstly, they polished the mirrors to a level that is pretty imperceivable to me, right? So if, for example, if Colorado was the same smoothness as the mirrors of Chandra, then the highest peak in Colorado, so Pikes Peak, that would be about 1 inch tall. That's how smooth these mirrors need to be able to actually focus X-ray light in the first place. Secondly, you need them to be reflective of X-rays, because it's all well and good a few X-rays getting through, but that X-ray light is our signal, right? We need as much of that signal as possible, and so there's a clever trick that X-ray astronomers use, which is to coat your mirrors in iridium, which just at X-ray wavelengths, it just happens to reflect the most X-ray light that we know of. Then secondly, or thirdly, assembling the mirrors in the first place was an extremely challenging job, right? So just for the record, the Chandra instrument, because you have to achieve these grazing mirrors, where the photons are skimming the mirrors, you need it to be very long. So the Chandra instrument's about 2 meters long, 2-3 meters, and the mirror assembly, for assembling this 3 meter long thing, they had to be precise enough or correct enough to the level of 1/50th of a human hair. That's how well they had to assemble these mirrors to be able to actually produce X-ray images from these focused X-ray photons. Now, in terms of actually deploying Chandra, I believe it holds the record as the biggest and possibly heaviest thing that the Space Shuttle has ever deployed. So Space Shuttle Columbia deployed Chandra. Here's an image of its launch in 1999 in the summer. And Chandra is also very special because it's on a very elliptical orbit. And I only actually recently found out one of the reasons that this orbit was originally proposed. It's in an orbit where it goes very close to the Earth inside its radiation belts, but then on its furthest distance, it's about 1/3 of the way to the moon. So a huge quantity of distance. Now, one reason to do that is because you have long periods of time where you can observe patches of the sky uninterrupted for hours, which, as it turns out, for a lot of X-ray astronomy, you need that because it's a very photon-starved field of astronomy. But another reason that people did that was because of budget cuts. So originally, Chandra was proposed to be a permanent observatory in the sky, much like Hubble is, where you can continually service it for long periods of time. But that costs a real lot of money, right? And so when the team was creating the Chandra sort of concept and they put a proposal in, they had to change the orbit so that they could prove that it would be unserviceable, just to save money, right? And so how do you prove that you won't need to invest lots of money into servicing the instrument that you're building? Well, the answer is to put it in an orbit where you could never service it, right? And so that's actually why it ended up being on such an extreme orbit in the first place. And it's been there for 25 years now, uninterrupted, and still doing incredible science. So in terms of some pretty crazy science, I just wanted to put it into context what this means with this improvement in imaging quality. So this is a supernova remnant, just like what Margaret was talking about earlier. And this is the leftovers of a star that's basically exploded. Okay. So on the left, I'm showing the previous best imaging quality before Chandra from the ROSAT instrument, where you can see some features of the diffuse emission on the left. Okay. Now, in 1999, Chandra took a fairly shallow, not a long exposure of the same supernova remnant, and it's pretty crazy, the change in signal to noise that you can see. But I just wanted to note that for the first time, Chandra was able to actually resolve the individual neutron star at the center of this stellar explosion. This point source you see at the center, that's not a little blip in gas, that's literally the neutron star, the leftover of this massive star that's exploded however many hundred years ago. And this just in, as of 2019, this source has been observed so many times with Chandra over the years that they actually produced a movie. So if you look close enough, you can actually see that the gas on the right is actually moving, and you can actually see the turbulent structures of this supernova remnant moving with time. So, which I think is pretty crazy. Also, probably an equally famous supernova, or leftover of a supernova, is the Crab Nebula. Scientists believe this is the leftover of a supernova that was actually observed in China in sort of 1050 AD, I believe. But yeah, quite a few hundred years ago. And on the left, again, I'm showing the previous best from ROSAT, where you can see some structure. It's very good for an X-ray instrument. Modern day instruments other than Chandra, I should say, also struggle to do better than this, right? This is pretty incredible as it is. Now, as of 2018, it also turns out that X-ray astronomers, for whatever reason, love to observe the crab as a calibrator, even though, as you can see on the right, it is extremely variable, right? So they like to calibrate their instruments on something that actually varies quite a bit. But anyway, the same as before, we have quite a high definition image where you can see the central neutron star, you can see gas around it, and you can see jets coming out. But on the right, you can see a pretty crazy movie where you can see this gas moving and the material coming out as a jet temporarily over the matter of months to years. So what does this mean for the X-ray background? Okay, so this tile in the center is a pretty incredible image. This is 81 days of exposure with Chandra on the same patch of the sky, continually summed up for 81 days, staring at an individual source. Right? This holds a record, which I'll explain a bit more about in the next couple of slides. This area on the sky, just for the record, is about the same as the full moon. And as you can see, this kind of Chandra has answered the question. Right? This kind of shows you that if you stare at a patch of the sky with good enough resolution, you will detect the individual point sources that give you your X-ray background, right? And so this image is actually 80 to 90% of the X-ray background being resolved into point sources for the first time, which is, yeah, pretty incredible. And this is only capable at this sort of level, at these energies, because of Chandra's exquisite angular resolution. But what are those point sources? Okay, so there's just two more slides. So this shows an overlay of that same patch of the sky, the same Chandra Deep Field South. So on the left is a zoom in of the Chandra image, and on the right is an optical image where you can see all these beautiful galaxies. And it turns out if you overlay the left-hand panel onto the right-hand panel, all of these X-ray points, they perfectly coincide with the centers of a subset of the galaxies shown on the right. And it took a little bit of time for astronomers to realize that every single one of these points is an accreting supermassive black hole. And so the record that this image holds a lot of records, but it actually holds the record for the most accreting supermassive black holes in one image. There's about 5,000 just in this image alone. And yeah, every single one is just an accreting supermassive black hole, but at a different period in time, because it's taken different times for those photons to arrive to Chandra. So that was everything I was going to go over. But yeah, I would be happy to take any questions.